Alright, let's do a kind of start to finish example of using MPLab to put in some code, simulate it, stimulate the inputs, look at the outputs, and so on and so forth. So let me go ahead and start a new project. So I'll say File, New Project, and I'll go ahead and do a pick. F1220, and we'll simulate it, and we'll use MPASM, and I'll call this Demo 1. And then I'll go under source and I'll say new assembler file. I'll call it main. And let's just go ahead and write this. So include P18F1220.inc, origin 0, move LW7F, so we'll set 7F into ADCON 1 so that we're doing all digital I/O. And let's sample code. Let's read from port B, bits 3 through 0. And let's write to port A, bits 3 through 0. And we'll do that forever. Alright, so let's do some setup. We need to set up port A as an output. So let's move F0 into the W register. Move that into tris A. So those are outputs. Port B is an input by default, but we could also, go ahead and explicitly set tris A. Sorry, tris B. So we'll set tris B to be all ones. That makes each pin of tris B an input pin. And so now let's start our loop. So let's read from port B into W. Let's complement actually let's just do an XOR. Toggle the lowest 4 bits. And we'll clear the upper 4 bits. So we're doing some bit masks here. And then let's move WF into port A. So we'll send that to the output. And then that's the end of our program. So let's see if this compiles. Pretty good. The other thing we're going to want to do is this config statement up in the top. So we'll do our config. Watchdog timer equals off. Low voltage programming equals off. And that stops it from timing out after a few cycles and resetting the processor. So the main thing we need is config watchdog timer equals off. Okay, let's go ahead and compile that, and we can run it, and it runs, right? We can see that it's doing something, but it doesn't really tell us what it's doing. So let's add some stimuli, and let's look at the outputs. So first thing I'm going to do is window and simulator and stimulus. And I want to be able to change port B, bit 0, 1, 2, and 3. So I'm going to do RB0, and I'm going to have a stimulus for setting it high, and I'm also going to have a stimulus for setting it low. And then I got to do the same thing for RB1. And the same thing for RB2 and RB3. Alright, so high, low. Put these in the other order opposite. So low, high, low, high, low, high, low, high. This might seem like a pain to do, but it will be worth it in the long run. Alright, so I also want to look at the value of port A, because that's where we're sending our output to. So I'll go debugging and variables, and I'll enter a watch for port A. Alright, so I'm going to take my stimulus window and I'm going to drag that up here. And I can make this output window a lot smaller. And I can make my stimulus window a little smaller. So actually, I'll leave it like that. Alright, so I'm going to go ahead and just hit a breakpoint right here. And I'll go ahead and run. Bring this back to variables. And let's see if I can under I was hoping I could change the radix of this, but I'm not going to get too fancy. Alright, so port A is our output, port B is our input. So I'm going to start hitting F7 and stepping my simulation, and as you can see, it's just constantly reading from port B, complementing and sending it to port A. So my my output is 1, 1, 1, 1. My input is 0, 0, 0, 0. Now, if I set bit 0 of port B to be high, I should see bit 0 of this output going low, and sure enough, it changes to an E. If I set bit 3 to be high, then bit 3 should go low, and this should change from an E to a 6. So the output is the complement of the input. Now I could add another watch here, enter a new watch, and I could say let's look at port B, and I can see what's happening. Port B is equal to 9, port A is equal to 6. So let's go ahead and toggle bit 0 of port B. So we'll set this low. So port B should change to an 8. Up, port B, set it low. So port B becomes an 8. And when we toggle that, this should change port A from a 6 to a 7. So that's just an example. The details of the code aren't super critical. The idea is, you can set this up so you don't have to do a lot of clicking around and looking at things, right? I've got all of my stimuli up here. I can automatically make it low or high. I don't have to change what my action is. I can look at my outputs at the same time that I'm stepping through the simulation. I can keep stepping through the simulation, and I can change one of the inputs, and I can see what happens in response to that. I can go ahead and make all of my inputs high. And now port B is all 1s, and when it gets to port A will change to all 0s. So set up your environment in a way that works well for you, so that you don't spend a lot of time trying to figure out what you're looking at, or clicking around from one window to another. Try to set it up so that everything you need is available in one view, and concentrate on thinking about your code rather than thinking about, wait, did I set port B to be high or low? Because if you set this to a toggle, you don't know what the value is unless you remember each time that you toggle what the new value is. So take the time, set up a high and a low for each pin, and then you can say precisely, oh, I want bit 2 to become high. I'll just go ahead and fire that, and now or bit 2 to go low, and now it goes from an F to a B, and then port A changes from a 0 to a 4. Oh yeah, one other thing that can be useful with this will be especially useful in the lab where we start playing with timing circuits. We have a logic analyzer available inside MPLab, so under Window I can say Simulator and say Logic Analyzer, and I can look at signals across time. So click on the Settings option, and let's just go ahead and look at RA0 and RB0. And if I go ahead and I run this, and I look at my logic analyzer, and I start stepping through in time, I can see that RA0 and RB0 are both 0, but eventually RA0 rises high, right? Remember, this is our basic behavior: read from port B, complement, send it to port A. So port B is low, port A is high. Now if I take RB0 and I set it high, I step once, twice more, RB0 goes high, and it reads that, it complements it, it masks out the high bits, it sends it to port A. At this point, we see that port A goes low. And sometime later, if I set RB0 to be low, same thing happens. RB0 drops, RA0 rises. And so we've got, like a timing diagram set up now, and we can actually see in terms of instruction cycles when different things happen. And for example, from 15 to 20, that's 5 instruction cycles. From 39 to 44, that's 5. So it takes 5 instruction cycles when we change RB before RA changes, depending on where we are in the loop. So if I come up here and at this point I decide to set RB0 high, it's going to take a little more time for RA to respond. In this case, from 61 to 68, it took 7 instruction cycles, right? Because I changed my port B value while I was already inside this loop. And it's 5 instructions after we notice the value of port B that we can change port A. So we can start understanding the timing of our code a little better sometimes with this kind of approach. And like I say, a future lab 5 will be playing with timing, and this will be extremely useful. So it's a good tool to play around with early. All right, thanks.